I'm Dr. Jim Zoval. You're about to watch one of my video lectures. If you like this video and would like to get videos for your entire General Organic and Biochemistry course, you can do so at www.zovallearning.com. I'll give you more information about that at the end of this video. In chapters 2 through 5, you learned about pure substances. You learned that pure substances could be classified as either elements or compounds. Elements exist as either metals, for example, solid gold or solid aluminum, single element molecules such as H2 or O2, single element covalent networks such as carbon, and the noble gases such as helium and argon. Compounds consist of two or more elements. You learn that compounds are classified as either ionic compounds or covalent compounds. Examples of ionic compounds are sodium chloride or potassium nitrate. Examples of covalent compounds are H2O and CO2. Most matter on Earth is not composed of just one pure substance. For example, salt water, soil, milk, plants, animals, and air are all mixtures of pure substances. Except for subatomic particles such as electrons, all matter can be classified as either pure substances or mixtures. When two or more pure substances are combined, we refer to the combination as a mixture. In this chapter, you'll learn about three types of mixtures: solutions, colloids, and suspensions. Many medications are administered as solutions. Some are also administered as colloids or suspensions. In the healthcare field, an understanding of mixtures is very important in order to know how much and at what rate medicines should be administered. One way in which mixtures are classified is by their macroscale, visually observed homogeneity. A homogeneous mixture appears to be the same throughout the entire sample. These videos are made to be viewed while using fill-in lecture notes. The pause in the audio is to give students time to complete the lecture notes fill-in. The lecture notes can be downloaded, free of charge, at www.zovallearning.com. If you dissolve a spoon of sugar in water, the resulting mixture would be homogeneous. If you were to repeatedly withdraw one drop of the sugar water from various random regions in the glass, each of the drops would be identical. This can be contrasted with a heterogeneous mixture. A heterogeneous mixture has visible regions of varying composition. An example of a heterogeneous mixture is a chocolate chip cookie. In some regions of the chocolate chip cookie, a chocolate chip can be seen. In other small regions, a chocolate chip is not seen. A bit earlier in this video, I told you there are three types of mixtures: solutions, colloids, and suspensions. I'll discuss solutions first. Solutions are mixtures of pure substances in which the pure substance particles, the molecules, ions, or noble gas atoms, are evenly distributed throughout the entire volume of the mixture. The pure substance that's in the greatest abundance is referred to as the solvent. Typically, in biological systems, the solvent is water. The other pure substance components of a solution are called the solutes. With very few exceptions, the solution takes the same physical phase, that's gas, liquid, or solid, as the solvent. The solutes are said to be dissolved in the solvent. Solutions can be gas phase, liquid phase, or solid phase. An example of a gas phase solution is air. Air is a mixture of several gases, mostly nitrogen, oxygen, and carbon dioxide. An example of a solid phase solution is brass. Brass is a mixture of copper and zinc. When one solid, such as zinc, is evenly dispersed in another solid, such as copper, the solid solution is called an alloy. We'll focus on liquid phase solutions for the remainder of the course. There are three types of liquid phase solutions. 1. A gas dissolved in a liquid solvent. 2. A liquid dissolved in a liquid solvent. And 3. A solid dissolved in a liquid solvent. An example of a gas dissolved in a liquid solvent is carbon dioxide dissolved in water. This is how beverages are carbonated. Another example of a gas dissolved in a liquid solvent is O2, oxygen gas, dissolved in water. Fish extract the oxygen from water using their gills. Whenever a gas is present above a liquid, some of the gas will dissolve in the liquid. An example of a liquid dissolved in a liquid solvent is ethyl alcohol dissolved in water. This is the basis of adult beverages. An example of a solid solute dissolved in a liquid solvent is table salt, sodium chloride, or table sugar, sucrose molecules, dissolved in water. Most of the solutions used in biological applications, such as in biomedical analytical labs and research labs, are liquid phase solutions. For the remainder of this course, I'll use the term solution to mean liquid phase solution. Check your understanding of solutions. If the following pairs of pure substances are mixed in the ratios given to form solutions, identify each substance as either solvent or solute. Click pause and work on the problem now. The pure substance that is in the greatest abundance is referred to as the solvent. The other pure substance components of a solution are called solutes. For part A, there's more water than there is sodium chloride, so water is the solvent and sodium chloride is the solute. For part B, there's more water than there is ethyl alcohol, so water is the solvent and ethyl alcohol is the solute. For part C, the solute is water and the solvent is acetone. This is because there's more acetone than water, therefore acetone is the solvent. Another term for dissolving is dissolution. In liquid and solid phase solutions, the solute and solvent particles are attracted to each other by one or more of the 5 types of non-covalent interactions. The stronger the solute-solvent interactions, the more solute that can be dissolved. Let's consider the dissolution of ionic compounds using sodium chloride as an example. Sodium chloride, we know from our experience, you put it in water and it appears to disappear. Well, the sodium and chlorides are still in there, we just can't detect them with our eye anymore. How do they exist when we say they're dissolved? So we're getting an idea of what dissolved means on the scale of the individual ion or molecule. When ionic compounds dissolve, the ions dissociate, that's become separated from each other, and enter the liquid phase solution. In a sodium chloride crystal, the sodium ions and the chloride ions are held together with ionic bonds, as shown in this illustration. When the crystal is placed in water, these ionic bonds are replaced with non-covalent interactions between the ions and the water molecules. The water molecules surround the sodium cations and chloride anions on the surface of the crystal and displace the ions into the liquid phase. The water molecules and ions are attracted to each other through ion dipole forces. The partially negatively charged ends of several water molecule dipoles are attracted to the positive charge of each sodium ion, as illustrated here. Likewise, the partially positively charged ends of several water molecule dipoles are attracted to the negative charge of each chloride ion. We use the term solvation to describe a solute particle becoming surrounded by solvent molecules. Solvation causes dissolution of the solute. I'll show you what happens in 2 dimensions, but you guys think of this as 3 dimensions. The same thing happens in 3 dimensions. You have that interaction, positive and negative. When there's an electrostatic attraction, things will move, and this is what you get. So sodium exists in water solvated by a sphere of water molecules. There's actually like a second sphere also. People spend their careers studying the exact organization of water molecules around particular ions. Let's consider the chloride. It's not positive, but it's negative. The difference will be the other end of the water molecules will be attracted to it, and you'll still form the sphere of hydration, but with the other side of the molecule, with this side, watch. This is 2-dimension, but this happens in 3 dimensions. You just learned about the dissolution of ionic compounds. Now let's consider the dissolution of molecules, covalent compounds. Molecules will dissolve in a particular solvent when the solute-solvent non-covalent interactions are strong enough to overcome the solute-solute interactions. Unlike ionic compounds that dissociate, when molecules dissolve, the individual molecules become solvated. As an example, let's consider the dissolution of ethyl alcohol in water. Ethyl alcohol dissolves in water because it has significantly strong non-covalent interactions with water. These solute-solvent interactions enable the solvation of ethyl alcohol molecules by water molecules. Hydrogen bonding, dipole-dipole forces, and London forces occur between ethyl alcohol and water. Since water molecules are relatively small, the London forces between water and ethyl alcohol are not very strong. If they were the only non-covalent interactions present, ethyl alcohol would not dissolve in water. Ethyl alcohol's lone pairs can form hydrogen bonds with a hydrogen bonded to oxygen in water, and vice versa, as indicated by the green dashed lines in this image. Since ethyl alcohol and water are polar molecules, they can also interact through dipole-dipole forces. The dipoles of ethyl alcohol's highly polar bonds are indicated by the orange dipole arrows, and water's molecular dipoles are indicated by the blue dipole arrows. Note that in the case of both the dissolution of ionic compounds and molecules, I've shown you 2-dimensional illustrations of solvation. In reality, water molecules completely surround solvated ions and molecules to create what's called a hydration shell or hydration sphere. Because of the relatively small size of solvated molecules and ions, the forces imparted upon them from collisions with solvent molecules are much greater than the force of gravity. It's for this reason that solvated ions and molecules don't settle to the bottom of a mixture, but instead move in random directions in between collisions. This type of random, chaotic movement is called Brownian motion, and results in the solute being evenly dispersed within the solvent. Since ions and molecules are evenly dispersed within the solvent, solutions are homogeneous. Solutes that are polar are capable of dissolving in polar solvents. Solutes that are nonpolar are capable of dissolving in nonpolar solvents. This phenomenon is summarized in the easily remembered phrase, like dissolves like. Now I'd like you to work on a couple problems to check your understanding of the dissolution process. If you dissolve 1 mole of the following substances in water, how many moles of solvated ions would be present? Include both cations and anions in the number of moles of solvated ions. Click pause and work on the problem now. Check your answers. In part A, if 1 mole of sodium chloride was dissolved, there would be 2 moles of solvated ions. Sodium chloride is an ionic compound, therefore it dissociates when it dissolves. For every 1 mole of sodium chloride dissolved, the solution will contain 1 mole of solvated sodium ions plus 1 mole of solvated chloride ions for a total of 2 moles of dissolved ions. In part B, if 1 mole of barium chloride is dissolved in water, it would result in 3 moles of solvated ions. Barium chloride is an ionic compound, therefore it dissociates when it dissolves. Note that barium chloride contains 2 chloride ions for every 1 barium ion. For every 1 mole of barium chloride dissolved, the solution will contain 1 mole of solvated barium ions plus 2 moles of solvated chloride ions for a total of 3 moles of dissolved ions. The number of moles of ions that are dissolved in a solution can have important biological effects. For example, it will affect the way nerve cells can transmit electrical signals. Try another problem. In this problem, I want you to list all the non-covalent interactions that could occur between solute and solvent for each of the following solutions. You may find it helpful to go back to Chapter 4 and review the 5 types of non-covalent interactions. Click pause and work on the problem now. Check your answers. In Part A, for oxygen gas dissolved in water, hydrogen bonding and London forces occur. London forces can occur between any 2 molecules. Hydrogen bonding occurs between the hydrogen that's bonded to oxygen in water and a lone pair on an oxygen of the O2 molecule. In Part B, carbon dioxide gas dissolved in water, hydrogen bonding and London forces are present. Hydrogen bonding occurs between the hydrogen bonded to oxygen in water and a lone pair on an oxygen atom of CO2. In Part C, potassium iodide dissolved in water, ion dipole forces are the only non-covalent interactions that are present. Since potassium and iodide are monoatomic ions, we don't include London forces. For Part D, pentane dissolved in octane, London forces are the only non-covalent interactions that are present. The only way that hydrocarbons can interact is through London forces. The larger the molecules are, the stronger the London force attraction. Because pentane and octane are large molecules, the London force's attraction between them is relatively strong. You can get your entire general, organic, and biochemistry course as a series of video lectures. The rental period is for 1 year, so you'll have these video lectures for the entire term of the course. You could watch the videos whenever and however many times you wish. I survey my students and they prefer these video lectures over the textbook by a ratio of about 10 to 1. Fill-in lecture notes and an electronic version of my textbook are available free of charge at the website. To get more information or to get the videos, free textbook, and free lecture notes, visit my website at www.zovallearning.com.